Alright, let's sketch the function f of x is equal to 2x minus 2 times x minus 4 squared times x plus 1 with attention to degree, terms, intercepts, order, local and absolute, minimum, maximum, and domain and range. Okay, so let's start by looking at, first of all, the leading term of this function, right? So we can notice that there's x to the power 1 here. If you square this, if you expand this portion, the highest degree would be x squared times x to the power 1. So normally you want to do this as 2 times x to the power 1 times x squared times x to the power 1. And this is going to give you a leading term of 2x to the power 4. Okay, so this tells us a few things, right? So you can think about your leading term as ax to the power n, right? Your degree here, n is equal to 4. Okay, so your degree is 4. This tells us that our maximum number of turns, which are the points of extrema, the maximum number of turns here should be n minus 1, so it should be equal to 3, right? This also tells a here is greater than 0, right? So if a is greater than 0, this tells us that it's positive. And because the degree here is an even number, right? This is a positive even degree function. So this is a positive even degree function. This tells us that we'll have similar n behaviors because all even degree functions have the same n behaviors, and the n behaviors would be in quadrants 1 and quadrants 2 because it's a positive even degree function. Okay, so now that we know that, right, we have our n behaviors, let's find our intercepts. Well, it's really straightforward to find your x-intercepts here, right, because we know that factored form is in the form of f of x is equal to a x minus r, x minus s, x minus t, and so forth, right? But in this case, the roots, or x-intercepts, are in the form of r and 0, s and 0, and t and 0. Okay, so we can find our x-intercepts by letting f of x equals 0, and if you do that, your roots here would be 2 times x minus 2 times x minus 4 squared times x plus 1 is equal to 0. So therefore, x can be equal to 2, 4, and negative 1. Okay, so those are your x-intercepts. Now, after you find your x-intercepts, you also want to figure out the behavior of the x-intercepts, right? So let's look at, so these are our roots, right? And then this is, the behavior of the x-intercept is characterized by the order or the power on each factor. And we're going to look at the behavior. Okay, so roots 2 and 0, 4 and 0, and negative 1 and 0. At 2 and 0, we can notice that, right, it's a power of 1, so this tells us that the order is 1. At 4 and 0, order is 2. At negative 1 and 0, for this factor, the order is also going to be 1. Okay. At 2 and 0, behavior, it should pass through it. So it passes through. At 4 and 0, it should be concave to that point. At negative 1 and 0, it should also just pass through that point. Okay. Now that we have all that information down, we can also figure out our y-intercept to complement our sketch. I'll just do that here in different colors so we can visibly notice it from the rest. The y-intercept, I'm going to let x equal 0, so I'm doing f of 0 here. And if I plug this in, 2 times 0 minus 2 is negative 2. 0 minus 4 is negative 4 squared. 0 plus 1 is 1. And you basically get negative 4 times 16, so it's like negative 64. So the y-intercept is 0 and negative 64. Good? So now that you have your x-intercept, your y-intercept, your order, the number of turns you would expect, let's create a sketch here. Okay, so remember that this is a quartic function, right? Similar n behaviors. Let's make a nicer sketch than that. Over graph. Okay, I'm not going to draw this to scale. Don't really have the space for that, but right, we just want to plot some of the key points here. Okay, so let's plot our intercepts first. Okay, so let's say that this is 2 and 4, and let's do, this is negative 1. Okay, so this is 2 and 0, this is 4 and 0, this is negative 1 and 0. Okay, and we also have a y-intercept. Let's say this is 0 and negative 64, right? And let's draw our trace. Let's do it in blue here. We notice that it should end off in quadrants 2 and end off in quadrant 1. So one of your sketches, your curves, are going to do this. So one of your curves are going to do this because the end behavior is the second quadrant, and it's going to pass through -1, and it's going to cross the y-intercept. Okay, so once again, guys, sketch, right? I would definitely recommend doing this in pencil. It's kind of hard to do this in pen, right? And then what's going to happen here is it's going to loop back up, right? It's going to pass through the 2, but then we know that at 4 it's going to be concave to this point. Okay, it's going to loop back up towards one of the end behaviors is going to be in the first quadrant, right? So this could be a potential curve. Sketch. Okay, so this is our sketch. You can see that there's similar end behaviors, positive infinity, right? And now we can actually see the presence of a turn here, there's a turn here, and there's a turn here, okay, at the x-intercept. All right, let me just think it'd be easier if I just do that. Okay, so there's 3 turns here. That's consistent with what we have algebraically, right? The only thing we need to actually kind of figure out is this point here, this x value of the turn, and its equivalent y value of the turn. Now, because this is an even degree function, we're going to have local maximum minimum, but more importantly, we're going to have an absolute maximum minimum. And let's actually mention that here, right? If we look at our domain, the domain is going to be consistent for all polynomials. X belongs to the set of all real numbers. There is no restriction on the domain, but the range here is going to be restricted because there is going to be an absolute minimum point, right? There is an absolute minimum at 0 and -64. Because of the fact that the leading coefficient is positive, you will have an absolute minimum. Now you can notice here, because there is an absolute minimum, all other points will be greater or equal to -64. So this actually restricts our range. Okay, so keep that in mind. We also need to figure out this maximum here. We can see that there is another minimum point. There's a local minimum at 4 and 0. Right? But we still need to figure out this maximum point. So to find this maximum point, what we need to do is we need to find the midpoint, right? So the x value of the turn here is 2 plus 4 divided by 2, which is 6 over 2, which is 3. And then you just do f of 3. Okay, so you do 2 times 3 minus 2, 3 minus 4 squared, 3 plus 1, and then you get 2 times 1 times -3 squared times 4, which is like 9 times 4 is 36, times 2, that's 72. Okay, so f of 3 is 72. So this point here, it doesn't, I know the sketch doesn't look too good, but you get 3 and 72 here. It's not too consistent with the sketch, right? So this is it's gonna be a much more higher peak, right? Once again, just a sketch, guys. So it's good to kind of just figure these points out algebraically, right? So we should also have a local maximum at 3 and 72. Okay, so that's our local and absolute minimum maximum. We have our end behaviors, we have our domain range. Basically, this is our completed sketch.